If you can hear me and you can see me, can you chat something to me in the live chat? Okay, everybody, we'll get started here in a few minutes. I'm just going to wait for others to show up. Okay, everybody, it's around 6 o'clock, so I think we'll go ahead and get started with this first ever live stream of a nano chat. I want to thank everyone for attending. I hope this comes across the way I intend it to. It's a bit strange being in a place giving a talk with no feedback, so we'll see how this goes. Hopefully it turns out okay. So I'm going to pretty much the entire time show the slides. There's no need to look at this more than you have to. So I'm going to switch over to the slides now, and we will begin. And at any time, if anyone has if there notices any technical difficulties, just put it into the chat for me to see. There is a bit of a delay on what I see and what I'm saying, so hopefully I won't get too far ahead. So, all right, so you're here to learn about the Fibonacci sequence and the golden ratio, what it is, how it's found in nature, how we can use it for different applications, and it's a pretty interesting ride that we're going to go down here. Just get this going. But before we get there, I just want to have two quick slides on what Nanotech NYC is. So my name is Jacob Trevino. I'm the founder and president of Nanotech NYC, which we started a few years ago. There's a few other folks who you can find on the website who really help a lot, and it really helped to grow this larger than I ever thought it would be. So Nanotech NYC is an organization aimed at sort of fostering growth and building a community for nanotechnology in the greater New York City area. We started off as a website where we host a bunch of different resources, whether it's facilities, whether it's people, whether it's events. We try to put as much as we can in there, sort of a one-stop shop for nanotech in New York City. We started NanoChats, which is this is the first virtual NanoChat, but typically we do this in person in various places around New York City, most times at a university, but sometimes in a more informal setting. And these are typically informal in nature. We try to make them approachable to not only a wide range of people within the nanotech community, but also people from outside the nanotech community. We get a lot of people come in who want to just learn about what it's being used for, what are the future applications, and that's great. We welcome them. We do social networking at an event called Nano Nights, and these are held around the city where we gather, we network, we have fun. It's a really friendly group. I highly recommend attending one of our events if you get the chance. We also have a blog, which you should probably check out if you're thinking about going into the nanotech field. We interview a lot of folks who are either graduate students or working in the field, and they sort of give their trajectory on how they got there and what their future plans are. And so it gives you a flavor of what it's actually like to work and study in nanotechnology. And over the coming year, we're going to start growing our volunteer efforts to do a lot of STEM outreach and education. Just a quick note on Nanotech Alliance, which is the parent nonprofit organization of Nanotech NYC. This we are still building, and we're hoping to expand the resources on that website for national and international audiences. If you're interested in either one, feel free to email contact@nanotechalliance.com. And in the comments, or in the details below, there are links for the various social media platforms and our website. So check that out. So without further ado, let's jump right into our talk. And so the talk mentions, the title mentions Fibonacci and the golden ratio. And these are two separate things that are intertwined mathematically. And in order for you to understand the golden ratio, I first have to start with the Fibonacci sequence. So I'm going to tell you about the Fibonacci sequence, where it comes from, how it relates to the golden ratio. We're going to go over some various myths and some truths in how it's used and where it's found. And then I'm going to try to spin this in a way that gives you a flavor for how it can be used in nanophotonics. And for my PhD at Boston University, we used the golden ratio to develop nanostructures for a whole bunch of a very wide variety of applications. And I want to give you a flavor of what those are and other applications possibly. So should be an interesting journey. So to learn about the Fibonacci sequence, we have to go back and start with Fibonacci himself. So his real name was Leonardo Pisa, or Leonardo Bonacci. I apologize to my Italian friends. And he was around back in the Middle Ages, in the Middle Ages, and he was effectively I'm sorry, not the Middle Ages. Yes, yeah. So around 1200 AD, and he was effectively the greatest mathematician of his time. He's known for the Fibonacci sequence, but he did a lot of other things that are really important and interesting. Fibonacci comes from the Latin Philus Bonacci, which is son of Bonacci. So it's not his real name, but that's what everyone knows him as. So what he did is he actually wrote this really seminal book called Liber Abaci. Again, sorry if I butchered it. But effectively, it's the book of calculations. And yes, he did introduce the Fibonacci sequence in this book, but what's also worth noting is that he actually introduced the Hindu Arabic figures, which we know today as 0 through 9, to Europe. Up until that point, effectively, the Roman numerals were used, and they didn't lend themselves very much very well to mathematical calculations. So he actually integrated the Hindu Arabic figures with the zero, the what they call Zephyr back in the day when it was first around, and with all these he could effectively write all the numbers which we know today. So that's in section 1. In section 2, he really goes over all these different applications of mathematical constructs that he wants to get out there, and he does a really nice job of using applications from commerce so that the people who read it can actually see how mathematics can be used and why it's important. An early SciComm individual, if you will. The third section is what we're really interested in here. Now this is where he discusses the growth of a population of rabbits using effectively what becomes known as the Fibonacci sequence. And so we'll start there. We're skipping over the fourth section. And it's this really interesting problem that he posed. It's very hypothetical in nature, as a lot of mathematical constructs are. What Fibonacci was posing the question in his book is, how many rabbits can a single pair produce after a year if they keep reproducing, right? And like any good problem, there are a set of assumptions, and most of the very ideal assumptions. So these are the rules, right? Rabbits are able to mate at the age of 1 month. Pregnancy takes 1 month. Rabbits never die over the course of this year. And a mating pair always produces 1 new pair, and that new pair has 1 male and 1 female, right? So very idealistic in the way it's set up. But the goal is to really describe this sequence, which will give us an idea of how many rabbits will be there in the end. So let's step through it, and slowly we'll tease out the Fibonacci sequence. So we start with these 2, slightly unbelievable adult rabbits, male and female, and they mate. And at the end of in the second month, they actually produce a pair, as we said before, and this pair is a male and female. And so we go to month 3, and in month 3, see if you can see my mouse. I think you should be able to hear. Yep. So in month 3, these 2 previously baby rabbits become adults. So now we have 4 adults, and the 2 previous adults have made another pair of baby rabbits. And then again, in the 4th month, same thing. These 2 grow up to add to the total population of adult rabbits, and there are now 2 new sets of baby rabbits, both obviously male and female, as we said before. Okay. So this goes on and on and on for 12 months. The end number is not what's important, but let's tease out the sequence now and sort of go over this one more time. So what I'm doing here is I'm calling in month 1 these 2 adults as A, as an adult pair, and so we'll note that here is 1 adult pair with no baby pairs, and a total number of pairs of 1. Again, in month 2, we now have these new baby rabbits, and so we note that down here as 1 and 1 with a total of 2. And then we continue this sequence on and on, this multiplication as we described before, and the rabbits start exploding, right? You start getting a large number of rabbits quite rapidly. And this is sort of the first time the Fibonacci sequence shows itself. So we're going to look at on the right-hand side here, the total pairs. And this is actually the sequence going from top to bottom. And so you'll see there is 1, 2, 3, 5, 8. And if anyone is experienced in mathematics and is used to looking at things like this, you might notice a pattern. And the pattern is you can generate one number, for example, let's say 3, by adding the 2 previous numbers. So 1 plus 2 equals 3, and so on. 2 plus 3 equals 5. 3 plus 5 equals 8. And the sequence follows in both the adult pairs and the baby pairs. So here you see 1 plus 1 is 2, 1 plus 2 is 3, and so on. And the same thing for the baby pairs. And so these numbers make up the Fibonacci sequence with this, adding the 2 previous to get the next one. You can describe that in words and via equations. So in words, it's such that each number is the sum of the two preceding ones, right? And mathematically, you can write it shown here if you're mathematically inclined and you're used to looking at things like this. That makes more sense. But the point is, why does this matter? Why should you care about the Fibonacci sequence? And the sequence itself doesn't have a ton of applications, but what's more important is rather its relationship to the golden ratio, which is what we're trying to get with this. And I'll explain that connection here in the next few slides. So let me give you some examples of first what the Fibonacci sequence is, where it's found and what it's used for, and what it can be used for. So this one is pretty interesting. I am an American. I live in New York City, and I'm used to miles. When my European friends, or actually anyone from outside the United States for that matter, ask me how far something is, we always have this conversation of trying to convert miles to kilometers. So let's just say, hypothetically, I want to convert 5 miles to kilometers. So what you can do with the Fibonacci sequence is you can take that number, 5 for example in this case, and then look at the next number in line to get the approximate distance in kilometers that it's equal to. So if you look at the actual value, it's 8.046272, which is pretty darn close. Let's do another one. Maybe we got lucky. Let's say 34 miles. So 34 miles. Look at the next one. It's 55 kilometers. The actual value is 54.717, and so on. And you can keep doing this indefinitely and use this as sort of a guide for of converting. And it was just really odd considering this number came from multiplying rabbits. And the first time I saw it, I was incredibly amazed that this was the case. And the question is, obviously, how is this possible? And I'm going to come back to this, I promise, but it has to do with its relation to the golden ratio, and we will get there. So let me give you an example of how the Fibonacci sequence plays out in real life, like not this idealized rabbit population problem. So we're all familiar with honeybees. We learned in school at a young age that if the honeybee colony, there is one queen bee, and this one queen bee is the only female to produce eggs. There are female worker bees, and there are male drone bees. But what you didn't probably know, and I found this to be interesting, is that not all bees have two parents, right? So the way it works is a male bee is produced by an unfertilized egg. So the queen lays eggs, and sometimes the males fertilize eggs and other times they don't. When they go unfertilized, they produce a male. What that means is that males don't have two parents, right? They just have a mother. Females, on the other hand, are produced sort of in the way that we're used to when the male bee fertilizes the queen's eggs, and every time that happens, you actually get a female. You'll never get a male in that situation. So males only have one parent, females have two parents. So the exercise that we want to do now is let's look at the family tree of a single male drone bee. Okay, so male drone bees in sort of the first generation. Going back one generation, we remember that you can only produce a male by an unfertilized egg, so that drone only has a mother, no father. That female, on the other hand, has a male and female mother-father pair. And going back now, we can keep stepping through, right? So female has a mother-father, male just has a mother. And we can keep doing this over and over and over again. And we can take this back as far as we'd like, but we'll stop here and we'll look at the different generations. And what we're going to do is we're going to count the number of bees, total bees in each generation. And if you do that, which is what I show on the right-hand side over here, you have 1, 1, you have 2, you have 1, 2, 3, and 5, and 8, and 13, and so on. And so if you look at the generation, the number of bees in each generation, you will always get a Fibonacci number, and they will follow the Fibonacci sequence, which is pretty interesting. it's actually embedded more than just in the total number, just like with the previous one where it was adults and babies. We can look at females, for example, just look at the number of females in each generation. Here there's one, here there's just one, here there are two, here there are three, and here there are five. And so this keeps going. And so the Fibonacci sequence is sort of embedded within itself. It's kind of meta in this example. So that's a real world example. Now I'm going to show you something that you've probably seen before. You probably didn't know that this is what it was called, but I'm going to introduce to you the Fibonacci spiral. But to do that, to construct the spiral, we actually have to start with these simple little building blocks. So let's start with the first two numbers in the Fibonacci sequence, 1 and 1. So all I've done is I've drawn boxes that are equal width and height to whatever their value is, their unit value. So this is unit value 1, and if I go to the next one, it's a 2, and I just stack it on top, and so 1 plus 2 is now, the next one is 3, and again, the size of this box is exactly 3 units, 3 of those little 1 units, okay? And I moved it to the left, and we're just gonna keep doing this in a way that we're going counterclockwise, and you'll notice that it fits very nicely it matches the one side that it's paired up against exactly. So that's 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, and 8 plus 13 is 21. So we created this nice color image, and some of you may actually have seen this before, but if you then take a effectively an inscribed quarter circle, you create an arc in each one of the little boxes, and what ends up being drawn is this golden spiral. Now I'm positive that you have seen this before somewhere. This particular spiral is called a golden spiral because it is created with the Fibonacci sequence, and this is also the first time that I'm showing you that the Fibonacci and the word the golden are related in somehow. But what is important to note is that this is a specific type of logarithmic scale, right? There are lots of spirals you can draw like with a similar method, and this Fibonacci just happens to be one generated with the with the Fibonacci sequence, but it is still logarithmic spiral. So you have to be careful because you will see this be sort of smushed onto all kinds of images where they claim that it is a Fibonacci spiral or a golden spiral. So this is a nautilus shell. You see that it has a similar path to this spiral shape, very close actually. And it is indeed approximated with a logarithmic spiral. It just might not always be the Fibonacci spiral or the golden spiral, right? Spiral galaxies. This one matches up really well, but there are several types of spiral galaxies, most of which can be approximated with logarithmic scales. Sometimes they happen to be matched with the golden spiral. Weather patterns also have the similar logarithmic spiral geometry to them. And you can see this one matches up very well as well. But I mean, you can imagine 2 seconds later, this radar map shifts and it no longer fits the golden ratio spiral. So just a caveat, they're not all specifically Fibonacci based, but the logarithmic spiral is something that's found in nature quite often. So you have to be very careful. You will find people shoving this golden spiral on top of everything. Here's Conan O'Brien doing a hair flip, and you can see that the water traces approximately a golden spiral. These are two of my other favorite applications that I've seen over the years. The good old Drake meme, and then a very round bear, and you see that you can overlay a Fibonacci spiral on them both very well. So be skeptical. All right, so let's more formally sort of make this connection. That was the first connection where we built this spiral using the Fibonacci sequence. So let's start again with our Fibonacci sequence and see if we can't come up with a golden ratio. So what I'm going to do is I'm just going to take the second number and I'm going to divide it by the preceding one, right? So in this case it's 1 divided by 1. And I'm going to do this for each one of the Fibonacci pairs. So 2 over 1 is 2, 3 over 2 is 1.5, and this will make sense in a minute. You'll probably, if you look at what the golden ratio, like the name, it's golden ratio, right? So you expect that this is going to be some sort of ratio, some sort of numerator and denominator pair. You can plot them effectively, and when you start plotting them, you'll see a trend happening as you go further and further and further, higher and higher into the Fibonacci numbers. And if I plot them on here, this is what ends up happening. They end up converging. And they end up converging on a very, very specific number. That number is what we call the golden ratio. So the golden ratio is this irrational number. It goes on forever, but effectively it's 1.618034, keeps going. You'll see it almost always denoted as the Greek letter phi. And conveniently, phi is the Greek letter for F, and F stands for Fibonacci. I don't know if that's why it's like that. Some people suggest it is. There are other potential connections between phi and Fibonacci. But this is the ratio. It inherently is generated from these ratios of Fibonacci numbers. And so just to connect back to the miles to kilometers part, the actual conversion from miles to kilometers is 1.60934, about something like that, right? And you can see that it's very close to the golden ratio. So that is sort of why you can use these Fibonacci numbers as an approximation of the conversion from miles to kilometers. And you could always go backwards too, right? You could divide the two the other way. So we have a number now for the golden ratio. Let's look at it in a slightly different way. So it's a ratio, right? So it's a ratio of one thing to another. So let's take two line segments of different lengths. We'll call the longer one A, we'll call the shorter one B, and the total length is the sum of the two, right? A plus B. So you can actually define these two sections as the golden section or a golden ratio if it follows this very specific rule. And that rule is A plus B is to A as A is to B. That's somewhat abstract when I say it the first time, but it's easier if you write it out this way. They're just ratios, and as long as they're equal, then you will always get the golden ratio, which is kind of weird to think about, but they could be arbitrary numbers as long as they follow this rule that A plus B over A is equal to A over B, and you will get the golden ratio. You can define it more rigorously mathematically as 1 plus the square root of 5 over 2, but it's not necessary if for the sake of this lecture. We're going to be talking about the golden ratio in terms of pairs of Fibonacci numbers and in segments that are equivalent to that are equivalent to the golden ratio. One thing to note for those more mathematically experienced folks is that this is an irrational number of the golden ratio. It is actually the most irrational number of all irrational numbers. That doesn't sound like a real thing, but it actually is. There's a mathematical proof that involves continued fractions, and effectively what it means is that this convergence upon the actual golden ratio is slower than any other convergence for an irrational number. So it's a real thing. So the golden ratio has some sort of, I don't know, they're not spooky, but they're weird places that it shows up. So we'll look at a pentagon, for example. If you look at the two sides of a pentagon, these two that I've shown here, and they're unit length 1 and 1, if you take a line that connects the two ends, it will always be the golden ratio, 5, every time. So pentagons inherently have the golden ratio built into it. Odd. Pentagram, which has all different kinds of symbolism. If you describe this one pink section here as the unit length 1. Then this blue one that I've shown you here will always be phi. Not only that, this green one that I show you on the other side will always be phi squared, and this top one will always be phi cubed. That's really odd and very strange to me when I first learned about this. And because it shows up in these very fundamental geometric shapes, people have always associated the golden ratio with some sort of inherent beauty, right? It's naturally there in all these cases. So there must be something special about it. So there's a lot of people that try to assign beauty to the golden ratio, whether it's with people, whether it's with art, music. We're going to talk about a few of these different ones. But let's talk about one somewhat ridiculous one first. So there's a group of folks who believe that the golden ratio is inherently can be used to tell who is beautiful, right? So if you look at this particular graph here, this woman's nose, if we set that to the unit length of 1, then if their lips are the golden ratio wide, then that is like the #1 score for nose to mouth width that you can get for someone that's supposedly beautiful. Here's another one over here where the height from the chin to the top of the hairline, or to the hair, is golden ratio when compared to this section of the lip down to the chin. Seems somewhat arbitrary to me. They can make these very complicated masks, which they claim are each one of these lines, with some relation to the golden ratio, suggests some amount of beauty. And so they run it in these algorithms, and they determine that Bella Hadid, who I have no idea who she is, she's very pretty, but according to this equation, she is the most beautiful woman in the world, according to the golden ratio. And so you see how she gets a score for each one of these things. And so, yeah, I'm going to say false. There is no scientific data to support any of these claims. What's the saying? Beauty is in the eye of the beholder. So this is a very wrong application of the golden ratio, but people do use it. One other application, one other place where people think it's found is in proportions of hands and arms and other parts of your body as well. But this one's a little more real in the sense that if you actually measure ratios of, for example, in this bottom picture here, your shoulder to your elbow and then your elbow to your hand, those are approximate golden ratios. It's obviously different because people are different size and shape, but the relative length actually always come out pretty darn close to a golden ratio. Same thing with hands. If you take these different sections that are shown here between the tip and this first point and the knuckle, medius knuckles, and then the wrist, you see that they're sectioned out by ratio 2, 3, 5, 8, which are Fibonacci numbers. And then for a stretch, 2 hands, 5 digits, 8 fingers that are composed of 3 sections. Yeah, I'm gonna say no. That one's a bit of a stretch. You'll see people trying to fit the golden ratio and the Fibonacci sequence into spaces where it really doesn't belong. But for the other ones, I will allow it because it is indeed. If you should do it. Measure your fingers and these ratios and see what you get. And I bet you get a pretty close ratio to the pretty close value to the golden ratio. So people have associated the golden ratio with beauty. People actually really love it in art and claim that art made with the golden ratio is inherently more aesthetically pleasing. So, but before we do that, I want to sort of frame the use of it in art by telling you about another old text that was written by Luca Pacioli, and this is back in 1509. And this is a book where his best friend, actually, Leonardo da Vinci, illustrated some of the pictures in it. And effectively what he was doing is he was describing what he called the divine proportion, which is the golden ratio. They discussed all kinds of mathematical proportions, where it's found, different applications, like we mentioned before, in geometry, in architecture, which I'll show you some examples of here in a minute, and the two really important things to note here, the one, he actually gave Fibonacci credit in the book for being the main source of sort of the mathematics behind the Fibonacci number and the golden ratio. And so that is when Fibonacci's name became sort of synonymous with everything. The other thing is this book made the golden ratio very popular, and from this point on you see it being used in a lot more spaces and people searching for it in different spaces. So just to put it in context, this was sort of a bump in popularity at the time. So let me give you an example of art, finding in art. So Albert Dürer, one of my favorite German artists, back in 1500. This is his self-portrait. It's a bit what would you call it? Arrogant in the sense that he sort of paints himself as Jesus, which is interesting. But if you look inside of it, he actually used, well, it is believed that he used the golden ratio to sort of size out different portions of the painting. So if you draw this triangle connecting his shoulders and his head, it splits the picture into a golden ratio when you look at A versus B. Additionally, if you look even more closely in ratios of his eyes to the tip of his nose, and there's several other ones in here, they actually very, very, very closely come very close to being golden ratios. So it's believed that he probably used this in his design. He would have known about it at the time, and in other pictures you can also find it. Sandro Botticelli's Birth of Venus has it all over the place, and this we know for a fact that Botticelli was using it. And so in some cases with all this art, there were places where people believe they were using it on purpose, and there are other cases where it's actually documented that they meant to do it because they believed that it was a sign of beauty or had some inherent meaning to it. So if you look at this, the entire painting is exactly a golden ratio, the length to the height, or the width to the height. And then if you cut the picture in various ways, for example, on the left-hand side here, I'm showing you that if you cut at the where the ocean meets the sky, to the top, that's B, and then from there down to the bottom is A. That's exactly a golden ratio. And on the other side, same thing with the seashell to the bottom, and then from there to the top, those are golden ratios. And so, and actually, there's actually, if you look up this painting and you look up golden ratio, you'll find that there are more proportions within Venus that are golden ratios. Da Vinci obviously was very well aware of it, and thought it was a very special number, incorporated it drastically into the Last Supper. It's found everywhere. Salvador Dali, in his version of the Sacrament of the Last Supper, also had several golden ratios picked out and placed. So same thing with the width of the painting to the height. Actually, there's an intersection that splits this painting into two golden squares that happen both by design at the apostles to the left and to the right of Jesus in this painting. And Salvador Dali noted, he actually said himself that he did this on purpose. So that's one we know. The golden ratio has been incorporated in the architecture going way back. And when I say way back, I mean as far back as we can look. Taj Mahal has it built in several different places. If you want to find these, if you want to look in more detail and actually see how these are split, and which ratios form the golden ratio, you can. But I just want to go through this pretty quickly. I don't want to spend too much time on it. But the cathedral with Notre Dame in Paris, the UN building actually has right here in New York City has various sections which come out to be golden ratios exactly, and the architect admitted that that's what he was doing because he found beauty. And the same thing with the CN Tower in Toronto, has golden ratios built in. The one that's really kind of shocking and impressive is if you look at the Pyramid of Giza, the Great Pyramid of Giza, and you take measurements of the pyramid itself and look at in this case, the hypotenuse that this right angle makes and the height. You'll notice that this is phi, which is the golden ratio, and this is the square root of phi. When you have this kind of triangle, this is called a Kepler triangle. You can model this structure with this, and it's incredibly close to being exactly a golden ratio. It varies by less than 0.025% of a perfect golden triangle, and that's just a difference of a few inches in the overall height and width of the pyramid, which is pretty amazing. If you look at the three great pyramids, and from the top down, and look at how they're sized and how they're proportioned in relation to each other, here's a sort of aerial view here with some light boxes drawn around each one, and then some different color boxes. And if you look over here, it's easier to see without the actual aerial view. These ratio out to almost exactly golden ratios, which is interesting because there's no record that the Egyptians had any idea about the golden ratio. At least there's no there's no documented record of it. But people always like to say, there's no way they could do this on their own. And clearly, it was aliens, maybe. But I will say that the Greeks knew about the golden ratio. They really were fascinated by it, and Plato wrote about it. And so it goes back pretty far. It's not documented that the Egyptians actually had the idea when they made the pyramids. I'm going to give you one example of music. There's lots of them. Again, same idea, some that are intentional, others that are suggested, or people think they meant to do this. This is Chopin's Prelude in C. So this is really interesting, and after I tell you about this, it's really cool to go and listen to it, because the points that I point out here are actually very obvious when you listen to the music. It starts with an 8-bar opening, right? 8 is one of the Fibonacci numbers. The first major chromatic event happens at the 13th bar, again, Fibonacci. The climax happens at the 21st bar, and the total piece is 34 bars long. Right, and it's a sequence of Fibonacci numbers. And it's neat to look at this picture and then also listen to it. It matches up incredibly well. This piece here, there is a record of, he wrote a letter to the person who was publishing the music sheet, and said that there was an error and that he had to adjust it. And the reason that he had to adjust it was because he wanted effectively for it to represent the golden, I forget how he referred it to, like the golden number or something like that. But he knew what he was doing when he made this. Other examples are Mozart's piano sonatas, Beethoven's Fifth Symphony, and there's lots of others. Again, some of them purposely did it. Others, they're just very, very, they're very well organized in a way that lends itself to being golden ratios or Fibonacci numbers. So there's a whole bunch of examples where it's found in nature, or it's found in art, architecture. You have some background on the Fibonacci sequence and how it relates to the golden ratio. I promised some nanophotonics in here. So I'm not sure the audience that's going to be watching this, and I assume that it is not a photonics community. And so I'm going to give you a brief introduction to photonics. I'm going to try to explain sort of the fundamental principles that we're interested in these applications in particular. Then I'm going to give you a very brief examples of how this is used, because I don't want it to get too deep into the details. But for those of you who are not familiar with nano or nanophotonics, let's jump into this very slowly. And so we'll start with the word nanophotonics itself. Let's split it into nano and photonics. And let's first just start with nano. This is Nanotech NYC, and so I should really give you an idea of what that actually means. So nano is a scale. Everyone knows it. It's very small, right? This is tiny, tiny, tiny. Specifically, it's nano means 1 billionth, and it's typically used with in the metric system with meters. So nanoscale implies nanometer scale. So that would be 1 times 10 to the minus 9 meters. And typically you'll see it with the symbol in, and nanometers is written out as nm. So I'm saying these numbers, 1 billionth, but does that really mean anything? Anytime anyone talks to you about nanotechnology, they're going to show you a slide like this, which tries to give you some perspective on this scale, because it's really difficult. And so on the top, these units are in meters, and on the bottom, these units are in nanometers, right? So over here is 1 nanometer. So tennis balls are 10 to the 8th nanometers. When you're around the micron range, which is 10 to the minus 6, you're looking at things that are, they're 1,000 times bigger than a nanometer, but the things that you're looking at are things like cells, grains of salt, something a little smaller. Nanometer really starts around, say, 100 nanometers, maybe a little bigger than that, but in this range is where you're looking at the nanometer range. COVID-19, for example, is about 100 to 150 nanometers in diameter. And when you start getting down to 1 nanometer, you're looking at things like protein and DNA. So I always like to give this example, one, because it's just, you know what a spider mite looks like, or you know what a mite looks like. It looks like a speck of dust, right? And two, because it's a super cool image. The folks at Sandia National Labs they love to put bugs on top of their devices and take an SEM image of it so that you can get a sense of the scale. So again, these are micro devices that are shown on the surface here, these different kinds of mechanical looking structures. So micro devices, those are 1,000 times larger than nano scale devices. And so this dust mite is about 250 microns wide. That's about, it depends on where you're from, but that's about the diameter of one of your hairs. That is 250,000 nanometers, right? So now you sort of have an idea of how small a billionth of a meter is. So let's look at the second part, photonics. Photonics actually has 2 parts. It has photon and it has the X part. Photon refers to light. It actually refers to the fundamental unit of light. It's both a wave and a particle, if that means anything to you. In the discussion that we're having here, you can think of it as a wave. It is photons are on that are visible light are on the order of, say, 400 to 700 nanometers, and that gives you from blue to red. The other part is the X part, and that actually is supposed to represent electronics. So it's actually it's photon and electronics combined is what photonics is. The whole idea behind photonics is that you're trying to replace what we typically use electrons for with a photon, with light, right? So where you're used to using electrons for things like sending signals, holding, it's data. If we hold electrons in one place, it's a 1. If it's not there, it's a 0. So there's a lot of effort to replace electrons with photons in these applications. And again, photonics, when we're talking about nanophotonics, you're typically looking at things that are manipulating or interacting with light in the visible spectrum, which is the light that we see. And again, this range anywhere from 350 to 800, 750 nanometers. And this is a little bit of a detail, but I think it's always nice for people who aren't in photonics to understand. So this is increasing wavelength, right? So this is the nanometer scale in here. That's UV light, that's below the visible light, and then infrared is beyond. Energy and wavelength are inversely proportional by this relation here. Wavelength is lambda. This is energy, E. And so what that means is energy actually decreases as you get longer wavelengths, right? So infrared light has less energy than visible light, and visible light has less energy than UV light. So it's just interesting to know. You hear a lot of people talking about how UV light can kill the coronavirus. That's because it is high energy. It is absorbed by the virus and can start killing it. So nanophotonics is everywhere. It's in many applications. The general idea is you are trying to make nanostructures which are on the same length scale as the wavelength of light you're trying to manipulate, and you want to then make it do things that it wouldn't normally be able to do, right? Because of the scale matching that happens. And so applications, for example, are things like fiber optics, data communication, right over here on the bottom left. In sensing applications, you find nanotechnology and nanophotonics. So all these tests you hear about for antibodies and for detect a virus, these are, a lot of them have to do with utilizing nanotechnology and nanophotonics. Energy applications, this is a solar cell, solar panels, making them more efficient. Things like LEDs have nanophotonics being used to make them even better. And so generally speaking, in nanophotonics, you can do one of two things. It's way more complicated than this, but this is a nice way to sort of group the applications into two big chunks. One is you can redirect light, right? So you can have light coming in, you have some nanostructure, the nanostructure turns the light or regenerates the light in a different direction. And that happens in things like solar cells and LEDs, which we'll talk about. Also like optical displays and optoelectronics. So that's redirecting light in the way that you want, that you wouldn't normally be able to do. And when I say that, I mean in a very small space, right? This is all happening in a few nanometers, tens to hundreds of nanometers thick material. The other application is to concentrate or trap light. We actually call it light trapping. And the idea there is you want the light to spend more time interfacing or interacting with whatever the material of interest is. So if it's a solar cell, you want to spend a lot of time there so that it gets absorbed more efficiently. If it's a sensor, for example, you're trying to sense some small molecule, you want the light to interact with that molecule as much as possible so that the signal that goes out is stronger. So this is very generic, but just think of it as either trapping or redirecting light in different ways. In order for me to sort of get to the final point, right, where I'm using a golden ratio or Fibonacci sequence to manipulate light in some meaningful way, I have to first describe what diffraction is. And this is going to be very generic, so I'm sorry for anyone who's actually a nanophotonics person out there. But let's see if we can do this in 2 slides. So this structure is like sort of a cross-section of, say, a piece of glass that has some nanostructures on it. They could be gold, they could be anything. They're opaque, effectively, and this is transparent. So if we shine light in, say it's a red light, say it's a laser, just a single wavelength of light. So red light comes in, as you know, it's scattered by the small particles that are on the surface. It could be even roughness would scatter it. But when there's a special case when these structures are ordered in such a way that they're periodic, right? The spacing between them is the same every time. And you can do this in 2 dimensions as well, and 3 dimensions, to be honest. But what happens with diffraction, in a sense, when there's a periodic structure, is that you get these diffraction orders, and we label them with M. So the 0th order is just most of the light that just goes through without being diffracted, and you get light diffracted in the 1st order at a specific angle, and then the 2nd order at another specific angle. And again, this is unique to things that have some order to them on the surface. And so if you change the light to now blue, you still get diffraction, but you get diffraction at different angles. But each one of those also has, we'll call it an order, 0th order, 1st order, 2nd order, and so on, right? So this structure that I'm showing you on its side, this is its cross-section view. These would be nanoparticles, and in this case, I'm showing you a top-down view of a 2-dimensional array of points. And this is just points, but they could be nanostructures that we arrange in this way on the nanoscale. And so here's an example of actually a real life example of this in practice. This is a laser coming out here. There's a chip that has these periodic nanostructures on it, and these dots that you see are actually the diffracted light. So these are diffraction orders, right? There's a first order, the second order, and so on, and you get this nice periodic structure. We can actually take this simple two-dimensional picture, and we can calculate what this image is going to look like. Right, here's an example where we have what we call the Fourier space, or this is the far field diffracted light. And I swear this is going to make sense. Just hang in there with me. So periodic structure gives you these specific diffraction pattern with these orders, right? And there's a special case where we're interested in what happens at a particular radius in this Fourier space, right? And this circle intersects these 4 points. That's called the Rayleigh cutoff condition when that happens. And what this means is light comes in, it interacts, it diffracts and scatters. And in this particular case, the Rayleigh cutoff condition, there's the first order gets diffracted in the plane of the array. So it actually does a 90-degree turn, and when it does a 90-degree turn in a space that's smaller than the actual wavelength of light. And so this could be useful for if we need to redirect light in a hurry in a thin film, right? And I'll show you the application of that in just a second. But so this is a special case, right? And this happens in this red line at these dots. And if we use the blue example, it would happen at a slightly smaller radius out, and you would have a dot here and a dot here and a dot here. But ideally, so let's step back. These 4 points here are this case that we see over here that happen at specific wavelengths, yes, but also at specific polarization. So light can be polarized, and I'm sure you've heard of polarized sunglasses. Light coming from the sun has all different variations of polarization, but something like a laser has a single polarization. And so these correspond to particular polarizations and particular wavelengths that this phenomenon happens at. So, why do we care, right? That's the thing you're asking yourself. Let me give you a scenario. So, let's look at traditional solar cells, right? Everyone's seen these on houses, in solar farms. They're quite bulky. You see they have these metal structures to support them, and it's kind of expensive to install these things, right? Because you have to go out and pour concrete and make space and all these things. What if we could make them super thin? And when I say super thin, I mean really thin. What kinds of things would that open up? So if we can make it so thin that it's flexible, think about making solar cells that are now pieces of clothing. They could power your devices, perhaps. You could hang them as curtains in your house, pulling energy from the sun. Lightweight solar cells to power vehicles. There's endless applications you can think of, right? And so why don't we just do this, right? Why don't we make solar cells super thin? There's a reason. What ends up happening, so let's look at this example on the left. This again is a cross section, and this would be the thickness of the cell right here. So the typical thicknesses are anywhere from 150 to 300 microns. That's pretty thick. That's something that's stiff, relatively speaking. And then because of that, light, as it passes through the material, has quite a bit of time to be absorbed, right? And if we make this structure super thin, like 300 nanometers, now this is several orders of magnitude thinner than this, right? It's so thin that it's flexible and transparent, there's not enough time for the light to be absorbed. So your solar cell effectively becomes considerably less efficient. So we can think of a mechanism where we employ that scheme that I mentioned before, where we put nanostructures on this surface, and as the light comes in, it gets redirected into the surface and into the substrate, into the material that's going to be absorbing. And as it travels perpendicularly, it has a long way to travel, just like it did here. It can travel for millimeters for a long time and have plenty of chances to be absorbed. So that's what we want to do. We want to design this effectively. So how do we do that, right? And this is where the golden ratio part comes in. And I have to introduce you to one more sort of abstract thing, which are Vogel spirals. Vogel spirals are a particular type of spiral, kind of like the one we saw before. However, it's a point pattern like the two-dimensional point that we saw, and it's named after Henry Vogel, which is where that name comes from. So Vogel spirals, the way we make them, let's step back for a second and remember the golden ratio, right? So we had this, remember we said we can do it as lengths, and we follow this rule, that's fine. You can actually create the equivalent golden angle, and you do it the same way, looking at circumference. A is to be, the same, you use the same rule, and if you do that, you get this angle that's 137.5, 0.07, blah, 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 right? That's an irrational number, just like the golden ratio. So just keep that in mind, that we can make a golden angle if we want to, just like a golden ratio. And then let me introduce you the Vogel spiral. So the Vogel spiral, what he did is, he came up with this simple equation. It's just a polar equation. So instead of having x and y, you have r and theta, right? So you can plot things this way with some distance from the center point at some angle from a reference, right? And the equation is really, really simple. This is just a constant. We'll just call it 1. Doesn't matter. N is going to be iterative steps. So it's just going to be 1, 2, 3, 4, 5, 6, and so on. In both cases, right? Here too. This phi is going to be a particular angle that we're going to input called the divergence angle. And I'm going to tell you about the special case where we actually use the golden angle. We plug that into this value here. And with that, we can then plot a two-dimensional plot. Let me just step you through this real quick. So say it's n equals 1, So it's just 1 times 1, or 1 times the square root of 1, right? Square root of 1 is the length r here, and the angle is going to be 1 times phi d. So it's just phi d. Now for n equals 2, the value goes from r to square root of 2 and 2 phi, and so on, right? Square root of 3 and 3 phi. So you can do this, and you can just go out to several n values and eventually create a really interesting pattern. And I'm going to show you, if this works, what ends up happening. So this is just n1, n2, n3 over and over and over again, going to higher and higher numbers. And this is a little bit trippy. It's going to start playing with your eyes a little bit. And hopefully you'll start recognizing a pattern. You've seen this before, right? Somewhere in nature. So I'm just going to fast forward along so that we get to the end. This is the final product after, I think it's 1,000 iterations. Oh, great. Let me just, technical difficulty. So what you end up getting is this structure here, which I just showed you on the previous slide. And it actually is a model for the distribution of seeds on a sunflower head. And so it's a two-dimensional pattern, right? Using the golden ratio. So sunflower pattern inherently has the golden ratio built into it, which is interesting. And you'll find it in several different places, right? You'll find it in cactus, the way cactus are oriented, the way pine cones. There's all kinds of flowering plants that use this. There's the arrangement of tree leaves coming from the top down. And so you'll find it many, many places, right? It's a conspiracy. No, it's not. I won't go into why and how that happens in nature because I want to stay with the photonics part, but you can look it up and it's pretty interesting how it happens. So this is the structure that we're going to use as our nanostructure, right? And real quick, I want to show you something interesting in how the Fibonacci sequence is actually embedded into the structure itself, right? So as you look at this structure, your eyes want to draw lines, right? You start seeing little arching arms that come from the center outward. And some of them go in one direction, some of them go in the other. We call these peristeces. And so I can actually connect these particles in such a way to highlight the different peristeces. So if I draw it this way, if you look inside here and you count the number of arms that are inside here, the number is 8. Now the other direction, if I draw it this way, there's 13. And this way, there's 21. And then this way, there's 34. And so on. And so these are Fibonacci numbers. And so there are embedded spiral arms in the Fibonacci sequence, which is really interesting and will come to play here in a little bit. And then if you also plot sort of the points for each one, so this was 0.1, 0.2, 0.3, 0.4, 0.5, and so on, and you start looking where the Fibonacci numbers are, you'll find them all clustered, and they converge again on a single line, which is really weird. And this really isn't important. This is just more of an interesting fact that they are converging on a particular line as the spiral grows. So, how does this array, this pattern, relate to my solar cell problem and to diffraction? So, this is a periodic array. This is its diffraction pattern that we calculated. And we want to, as I mentioned before, ideally populate this line, this circle, with as much light as possible, as many bright points as possible, right? And so you can use a random array, which is the extreme case, and you get this sort of disordered distribution of intensity. And yes, you could draw a line here and you have intensity, but that intensity is somewhat weak because it's distributed across all the space, right? You can now get fancy, and you can use these things called deterministic aperiodic structures. These are based on different kinds of mathematical constructs, inflation theory, L theory. There's a whole bunch. I won't get into it. Penrose is a particular pattern, actually is found in nature as well. Gives you something that is more like what we're looking for, more points along this circle, right? Another one called Danzer, which is similar to this disordered one, but you do get more of a circle involved. And if we finally get to the hero of the story, the golden angle spiral, you see that you have a very nice, well-defined line of intensity. So at all different polarizations at this particular radius, which corresponds to a wavelength, you will have this special in-plane diffraction condition yet, right? And so you can actually make different kinds of spirals using a different divergence angle. So this is the golden angle, 137.5. If you go just above it and just below it, you get variation of spirals with peristeces going in different directions. But they also could be useful in that they have this circular Fourier space. So, and we can go in and we can actually make nanostructures with this pattern. It's a process that's somewhat complicated. We're not going to talk about it here, but it's using top-down nanofabrication. These little points that you see here, each one of those is a gold nanoparticle that's 200 nanometers wide and about 30 nanometers thick, right? And we can precisely place them exactly where we want them. We can make them out of different materials, gold, silicon, we can make them different shapes, right? For all different applications. And so here's an example of using it actually to enhance the diffraction and absorption inside of a solar cell material. So you don't have to worry about the details, but effectively, this is a small little, you can think of it as a solar cell. It's actually a Schottky diode because there's a bias here for voltage. But it's the same idea. Light's going to hit this sort of beige part here in this square. It's going to be absorbed, and it's going to be converted at some rate to electricity, which we can measure out on a computer, right? And in this case, all we did was we put some spirals covering about 25% of the device area, so not even filling the whole space with it, right? And these are the similar ones that I showed you in the previous slide. And if you look at them under a high-angled light, they actually generate these really beautiful dark field images, which give you these crazy patterns, which are a whole other discussion. And we can test these with various spacings and various geometries, and we can compare them to our periodic array. I don't really want you to stress about these graphs, but what I want you to look at is down here. This is sort of the important part, is if you take the maximum integrated photocurrent, so that's the current that's generated from the photons being absorbed. You can enhance that photocurrent by 8% by putting a periodic nanostructure on top, right? And if you use the golden angle spiral, you can actually increase that photocurrent by 31%. This is compared to a flat surface a flat solar cell with no structures on it whatsoever. Right. So it's a good way. It works, right, in this sense. This is just a simulation showing my colleagues wrote some code to do this. It's pretty awesome. If you're interested, you can look at this paper. That shows the diffraction. And so you have its periodic structure on the left-hand side. You have, remember those diffraction orders, those very sharp, specific angles, and how it's different for red, blue, and green light, different wavelengths. And in the case of the golden angle spiral, you see that you get really nice 90-degree angled scattering, and across a broad spectrum you have really high wide angle scattering, which is perfect for solar cells. This is completely unrelated, but it in the sense that it's not nanostructured, but there is this solar array in Spain, and it's happened, they've used this a couple different places actually around the world to use these solar reflectors to reflect sunlight onto the same single point where there's a really efficient solar cell here, which then creates a ton of energy. They actually found that they could, if they were looking for the optimal shape of these mirrors and placing them in such a way that they don't overlap and get in the way of each other, it's actually the golden angle spiral. And there's a mathematical reason for that, but just an interesting application. You can actually use these spirals as well to enhance LEDs. So light works in both ways. Light can come down from the top and be scattered in the plane, but it can also take light that's in the plane and scatter it out of the plane, right? And so LEDs, as we know, LEDs are way more efficient than traditional light bulbs, right? But I doubt many of you know that LEDs are actually pretty inefficient in getting the light outside. They generate a ton of light in the material. So this is just showing you a cross section of, say, one point source of light. So it generates photons. Those photons go up, and the majority of them actually get totally internal reflected. So they get trapped inside the material. So only some get out. And so this is showing you the emission. So emission, light being emitted from this material, and being shined onto a screen. This is no structures at all. This is using a nanostructured surface to get a brighter image. And what happens is you can actually, these patterns, these nanostructured, in this case a periodic structure, help to extract the light. It's a little more complicated than that, but effectively that's what's happening. And so in the same way that we want this circular structures Fourier space for the solar application, you also want it for the LED application. And so these are just some other arrays that we compared the golden angle spiral to, and this is again the diffraction pattern just made fancier in red. And we can again make these in different kinds of nanomaterials. In this case, we're using erbium doped silicon nitride. And the reason we're using that is because the emission that erbium doped silicon nitride gives is at 1.54 microns. So that's infrared light. It's actually the exact wavelength that we use in all telecommunications, which is the end application of this, is making an on-chip laser for telecommunications. But it applies to LEDs, to lasers, everything. So a couple graphs, don't worry about them, not a big deal. What I really want you to see is down here. And so we're looking at, 10 times the emission enhancement at the wavelength that we're targeting, which is 1.54 microns, as compared to something that has no pattern on it whatsoever. And if you want to look at the graphs, you can see that the golden angle spiral has the highest enhancement compared to Archimedean and the pinwheel. And these they're related to how well they match up their different Fourier space. One last application real quick. This one is very heavy, so I'm going to really high level describe it. Talking about quantum encryption. So you can use quantum encryption with electrons, and you can also do it with photons. And so the way it works with photons is you have a laser beam, you have some material, whether it's nanostructures or some crystal, that it diffracts the light and splits it up in such a way that you have two photons that come through and that they're entangled, which means the information here is dependent on the information here, no matter if they're together or if they're split apart. And so this is, just ignore this. There's a way to analyze mathematically the golden angle spiral in such a way, for those who are interested, it's a Fourier-Bessel analysis or Fourier-Bessel decomposition. It's like the radial version of a Fourier transform. You can do it on the structure itself, and it spits out this plot with these particular peaks. And as you notice, the peaks that come out are at Fibonacci numbers, because we generated the spiral with the golden ratio. And so this is just structural. This has nothing to do with light. This is just purely a structural phenomenon, right? And again, these numbers are based on the Fibonacci sequence. Why that's important is because we want to see effectively, if we shine light through this structure, can we encode this information in that light? And the way we're going to encode it is with orbital angular momentum. This is a very abstract thing to try to explain, but effectively light can twist as it propagates, and depending on how many times it twists in a given wavelength, it has a different orbital angular momentum value. And that value, if it twists once, then that value is 1. If that twists twice, that value is 2, and so on. And so we want to see, can we actually encode orbital angular momentum values in the Fibonacci sequence in light that passes through these nanostructures? And so this is a setup, don't worry about it. This is, again, our tried and tested calculation of the Fourier space, just with some white lines circling, identifying the edges. The other thing that we have to take into account, but we haven't before, is the phase. Again, it's a very abstract construct within electromagnetic waves. Don't worry about it. Just know that it tells the complete story. There's both intensity and phase in light. This is calculated intensity and calculated phase after light passes through the spiral. And indeed, if you take this complex value, which this gives you, and you analyze it using the same Fourier-Bessel decomposition, you can actually find the Fibonacci sequence in the light that is scattered by these arrays. This is all theoretical. We actually went and made them and measured them. This is the measured value, this is the measured phase, did the analysis, and we were able to pick out most of them, 21, 34, 55, 89. This one was off a little bit, and that could be most likely test error or fabrication error. But you can actually encode information in orbital angular momentum in light that is scattered by these structures. Why is that useful? Well, we actually partnered with some physicists who specialize in quantum encryption, which I do not. And they were able to develop a quantum encryption protocol that used our spiral, which is here, light passing through the spiral, creating a Fibonacci sequence in OAM, and then split that up into the two different traditional quantum encryption paths. And as you saw in that original picture with the two entangled photons, and I'm not even trying to explain any of this, but just know that there is in theory, a method where this could be used as a very, very powerful quantum encryption method, generating high-ordered OAM. But we haven't actually done it. We did it. We were able to measure that the values exist, but we didn't follow through with the encryption. I'm not sure if anyone carried that on or not, but I left before I got there. So with that, I'm at 7:15. I'm going to stop. Thank you for letting me rant on about the golden ratio and Fibonacci sequence and spirals and art. Again, Nanotech NYC, this is a Nanotech NanoChat for Nanotech NYC. Follow us on Instagram, Twitter, Facebook, and LinkedIn. If you want to get in touch with me, or follow me on Twitter, here's my Twitter handle. You can go to my website and get my contact information. It's just jacobtrevino.com. I'm going to stop here, and I'm going to look in the chat section and see if there's any questions that anyone has. And if not, then we can end. But let me switch this over. Let's see if I can switch this over. Okay. So let's see. Questions. Tom, is the irrationality of the golden angle key to getting the continuous circular diffraction pattern versus discrete pattern? Yes. Yes, it is, as a matter of fact. It's the irrationality effectively prevents there from being periodicity, and the more ordered the particles or the point pattern is, the more diffraction peaks you get, right? So the light gets concentrated into those orders. So the irrationality helps a lot. So it being the most irrational gives you a more continuous circle in the Fourier space. There are disordered structures that can be optimized using these crazy algorithms to do something similar. Those are almost completely random. They're actually this entire class of point patterns called hyperuniform structures. So there's some folks at Princeton who are amazing at doing this. Hopefully that answered your question. Does anyone else have any questions? No? Well, how many spider bites were harmed in making this image? Jason, thank you. A few. No. It's a whole art to take pictures of as scanning electron microscope images of animals or insects. They obviously have to be sacrificed, but they actually freeze them in liquid nitrogen and then very quickly move them to the scanning electron system and take the image. Kendra, could this kind of tech be used to create other types of nonlinear optics? Yes. We looked at it, but we didn't really pursue it. There's nothing that's inherently obvious to the golden ratio that would give it a leg up on more conventional designs for nonlinear optics. We've done some work on it, and it can be used. Oh wow, cool. So Kendra tried to use geometric structures for rectifying diodes, but they never had enough nonlinearity. There's a whole field of really cool, seemingly disordered structures. They're this class of structures called deterministic aperiodic structures, where you're using these mathematical constructs like Fibonacci, Thumors, Rubin Shapiro. There's a whole bunch of them, and they all have unique properties. So any one of those could be one worth looking into for that application. So if there are no other questions, I'll go ahead and end. If you have questions, you feel free to email me. My email is just jacob.trevino@gmail.com. Happy to chat offline, and hopefully we'll do this again soon. Stay in touch. You'll go on the website if you haven't already and register for our mailing list. We'll send out a monthly newsletter, and we will keep you informed with other events that might be coming in the near future. So with that, I will sign off. And oh wait, Freddie. Sorry. Is the Fourier transform diffraction pattern showing the different frequencies in 2D arrays? What causes the spherical shape in Fibonacci Fourier? Yeah. So yes, the Fourier transform of the diffraction pattern, or it is showing the different spatial frequencies. That's what the Fourier transform is. It gives you the spatial frequencies of the pattern, effectively. So that's the K space. Yeah. Yeah. Cool. All right, everybody. Well, have a good night. Stay safe out there, and hopefully we'll see each other in person sometime soon. Alrighty.